Hello, in this video I'm going to go over some information regarding bits and bytes and why we refer to them when we're talking about types in C++, and just how much data they can hold. So on my right here I have what's called an ASCII table. An ASCII table is just sort of a visual representation of how our system interprets data. So as you can see here on the right we have a char, in the middle we have a hexadecimal value. You won't need to worry much about the hexadecimal value, but you will need to worry about the decimal value on the left. The decimal value is the integer value that will be behind the character value that the CPU will read once it's translated into binary. So what I mean by that is when we look at a character such as the uppercase A, the operating system and rather the actual CPU is not able to recognize what an uppercase A is. It doesn't know what that is. It may as well just be some sort of alien character. It doesn't know how to interpret that. So what the operating system does is it uses a translator to change the value into a decimal number. The decimal number will then be translated into binary, and then the CPU will be able to understand that binary value because it reads and writes in terms of binary. So most systems you come across within the past 40, 50 years or so will be using an ASCII table, or rather ASCII values behind characters. So you won't need to worry too much about another system using sort of a different thing other than ASCII, unless you're using something like an IBM mainframe from the 1950s. And so essentially, this is just how the computer translates data that we as humans can read into something that the CPU is able to read as well. So in here in my source file, I'm going to write some code to sort of exemplify this, and I'm going to include a library called bitset, which will just more easily print the binary value of data. You probably won't be using this in your classes, but I will be using it here in this example just to sort of make it easier to show the binary value. So I'm going to go ahead and do that right now. Okay, and then I'm going to create a character for the uppercase A. So here A is going to have the uppercase A value. It is a char type, which means it will actually store the uppercase A. However, in this example, I do want to print the integer value, or rather the decimal value behind A. So what I'm going to do is I'm going to change A's type, to an integer temporarily. I'm going to do that right now. Cout, and then int cast, and then A. What this is going to do is it's going to temporarily change A's type to an integer. So it's going to print the integer value of uppercase A, which in this case should be 65. And so let's do that now. And so as you can see here, 65. So the explanation here is that we have an uppercase A being stored in a char type. So this char will actually store the uppercase A in memory. However, we want to print the actual integer value of the character. And so if we wanted to, we could actually assign this to an integer. So we can say a number and then int A. And so that will do the same thing. It will assign 65 to a number, in this case, the numerical value of A. So let's go ahead and look at the binary representation of the uppercase A. So I'm going to go ahead and delete this over here, change this to, just type, set 8A, which is going to print the set of bits that are going to be in the A character. And so the reason why I picked 8 bits is because a char type is 1 byte in size. If we were to pick an integer, which is usually 4 bytes, we would need to do the amount of bits that are in 4 bytes. In that case, it would be 32, because there are 8 bits in 1 byte, and an integer is 4 bytes in size. But in this case, because a char is 1 byte in size, we only need to do 8 bits because there are 8 bits in only 1 byte. So let's go ahead and see what this looks like. As we can see right here, 0, 1, 0, 0, 0, 0, and then 0, 1, and that is the binary value that the CPU will be reading for the uppercase A character. This is also what we will see if, for example, we want to print the binary value of an integer. Let's just do int a equals 65. Because this is the decimal value of the character A. So let's see what that looks like. And as we can see, it looks the exact same because uppercase A is just another way of representing the number 65. And 65 is just another way of representing the binary value 0, 1, 0, 0, 0, 0, 0, 1. So let's go ahead and see what happens when we increase this to 66. And as you can see here, the last two bits have switched. The 1 is actually now on this side, and the 0 is now on the last side over here. And the reason why this happened is because as you get more towards the left, it goes into what's called the most significant bit and the least significant bit, which is over here all the way on the end. Without going into too much detail about that, because it's not really that important, essentially what happens is as the value increases, the bits that are turned on, which are the 1s, are going to shift more towards the left as your value increases. This is why if you want to print the value of 1, there is only going to be one bit that is going to be all the way over to the right, because that is the least significant bit, and you only need to have that one single bit turned on, which is going to be the 1 that is more towards the right. And so the bits that are turned on are going to be 1s. The bits that are turned off are going to be the 0. And so again, as you can see right here, when it was 65, pretty much it looked the same over here to the left, and the least significant bits, the 2 least significant bits over here, switched places. This is because it went up by 1 value. And so we can prove that by here, going back here and then printing the character value of uppercase B, essentially doing the same thing. And let's see what happens. And as you can see, the binary value is the same. Now, the reason why I didn't change this down here to 32 is when I was doing an integer is because for a low number like 65 or 66, if we wanted to print the full 32 bits, it wouldn't really even matter, because we would just have a ton of zeros all the way towards the left, and then these 2 1s right here more towards the right. And the reason why is it again goes back to the idea of that least significant bit over here and the most significant bit over to the left. The higher number you go, the more bits over towards the left that are going to be turned on. And it's because you need to have more bits in order to support bigger numbers. And so let's go ahead and exemplify that right now. I'm actually just going to go ahead and delete this line. And int a equals, let's just do that again. 65. Okay. And then go in here and then change this to 32. I'm going to write it and run this. And again, as you can see, it's a whole bunch of zeros over here all the way to the left. And it's because we're not using these. 65 is a really, really, really low number. We don't need all these bits over here to the left to represent 65. However, if we wanted to increase the number, let's just say whatever number this is going to be, we will start using more of those bits towards the left. And as you can see, because this is such a bigger number, the more bits we will need are shifted more towards left in order to accommodate for such a bigger number. And so because 65 was a really small number, even though it is an integer with 32, that is 32 bits long, we really didn't need all 32 bits. We only needed essentially the first 8 in order to represent the small number of 65. But again, if we want to do a much, much bigger number, then we will need more bits in order to allow for more of those bits to be turned on. So I do hope that you found this video at least a little bit helpful in understanding why computers, or rather why CPUs sort of put a value, a binary value, instead of just a decimal value, or rather just instead of just reading a character like we can, why it has to use binary instead, and how the operating system um, sort of takes a value that we can read as humans, such as the letter A or B or C. It takes it into a translates it into a number, and then it then translates it to a binary value that the CPU can read. So I hope this was able to help you in understanding that.